So anyways, as I was saying, this looks to be part of the reset circuit. So I'm fairly certain that this line here was some sort of either P good or voltage sense or something to tell the rest of the circuitry on this card, hey, power is up and ready to go ahead and start your program. So one thing I might do is when I pull that one down again, before I do anything, I might hook it up to a power supply again and try running that line high and low and see if one of those two states causes something to happen. Maybe they got like a built-in little hello world, you powered me on type program in the sign. Not expecting a whole lot, but it may be there. Crap. Why not just do it cool? Oops. Oh, this one I haven't even skinned the wires yet on. Oh, batteries are just uber nasty. Okay, here's a mess of grounds. Here's a mess of +5. And here's our mystery wire. Now, in the past I have tried taking it high, assuming it was some sort of voltage input. But it might be a P good signal, which is active low. Which would explain why, whenever I tried it before, it never worked. So first thing first, hook up the grounds. Hook up the power. Enable the power. Try taking this low. Nada. So, I don't think that had anything to do with the reason why this is not working. I mean, there's probably a reason why these were sitting in a junk box at a garage sale. Whoever had them probably got them for free, cheap, or whatever because they didn't work. And then either never got around to fixing them, or forgot about them, or got them thinking it was something easy, and it turns out it was not. Okay, back to the task at hand. Where was I? I traced reset. So after reset, DSR, DTR, RTS, DTR, those three, we know where they go. We traced them. So we're down to one pin. RXC. Oh no, we already know that. That one hooked from there to there and back to that ripple counter. So let's go look at the description of those real quick and find out what they are. Okay, so here is the definition of that TXC. Transmitter accepts parallel data, blah blah blah, converts it to a serial bit stream, inserts the appropriate character or bits based on the communication techniques, and outputs a composite serial stream of data on the TXD output pin on the falling edge of TXC. The transmitter will begin transmission upon being enabled. 0 to be held. Okay, so it sounds like this chip really does use the control lines above and beyond just putting them in the control register. So if you don't have your flow control bits right, it's not going to work. But it sounds like the TXC is the transmit clock. Transmitter empty. Oh, here we go. TXC. The transmitter clock controls the rate at which characters are to be transmitted. In synchronous transmission, the baud rate is equal to the TXC frequency. In asynchronous transmission, baud rate is a fraction of the actual TXC frequency. A portion of the mode instruction selects this factor. It can be 1/1/16. Okay, so yeah, that is definitely the transmit clock. And RXC is the receive clock. So that's the... So this was pre-integration, or this UART chip was pre-integration of the baud rate generator. So, you know, it had 3 gross modes it can be in. Divide by 1, divide by 16, or divide by 64. But to get, you know, today's UARTs, you can go into a register in them and set that register with all sorts of multipliers and dividers to get just about any baud rate frequency you want. Where this is sort of hard-coded to whatever comes in that clock chip. So I have the sneaking suspicion that this is taking this clock frequency somewhere along the line and dividing it down to a point that works with this UART to give them whatever baud rate they wanted coming out over here. Now, tracing some of this clock stuff through, the clock line also went over to this chip. So I wonder if this is dividing the clock down, this is dividing it down more, and then feeding it into him. I think that will be the next thing I trace out quick, because if it is, then I can pop those 2 chips off pretty quickly. Now, where is the clock? The clock input is used to generate internal device. Okay, so the main clock coming in has to be 30 times greater than receiver or transmitted data bit rates. So it makes sense that they had some sort of clock divider. You know, they had the main clock coming in from over here, which is running at frequency X. You know, I haven't traced the clock circuit completely out to know exactly what frequency they're running at yet. And then they take a copy of that and then use these 2 guys. This is an up-down counter, and that is just a, you know, sort of a ripple counter to divide it even more. Or I should say this is a binary counter. So I think that's my next order of business. So 169. So clock comes in pin 2 of 169. So I don't need him anymore. We're all done. 169. So yep, that's the clock pin. And then up, down is tied to up, so it's counting up. And then, oh, I say it's counting up, but I don't know that for sure yet. Let me, depends if it's tied high or low. It's tied high, so it's counting up. Now these pins, I got 2 tied high, 1 tied low, and 2 no connects. 1 tied high. These 2 are tied high, 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 high. No connects maybe, unless it's inside ground. What's ENP? Oh, they must be low to count. ENP, ENT must be low. Okay, so let's do some more beeping around. It looks like these 2 pins are not connected. Oh yeah, they are connected to each other. They're just not connected to... Oh. Okay. These 4 pins right here are the preload. So if you hit a special pin on this part, it will load this value directly into the counter. This is the clock input, so that's coming off the main oscillator. These 2 pins are enable, and they have to be pulled low in order for this guy to do anything, which they are. So he's always going to run. That corner pin is load, 4 outputs, and what's RCO? RCO... RCO looks like it's some sort of overflow. When everyone's low, it's low. And when everyone's high, it's high. I wish they had a description, an English description of what the pins were. Apparently it's some sort of like reload counter maybe? Yeah, that might be it. Oh, definitely. So this pin here, as it counts up or down, if the output of the counter is either all zeros or all Fox, it goes active. And I think it's active low. It's tied back into this pin, which is the load. So right now I think it's in count up, so when this hits all Foxes, this bit turns active, flogs this bit, which loads in the presetting here, which is 1100. So this is apparently a fixed clock divider. Now on the back side here, this pin goes to there, which is just ground. Yep. And where was it? Oh, and this pin here, the next one over, feeds into this other counter. Which that is one of the 4 counter outputs. In fact, it's the most significant bit of the counter outputs. So this thing's going to count from 1100. So from 3 up to 15, 1111, then reload itself back to 3 and do it again. And when it hits 0001, it's going to toggle the clock output to the next chip. I lost my spot. Because it's just hooked to that most significant bit of the counter. And that feeds into pin 1 of the 93. I don't see any other connections. That's a ground bus. So now let's look at the 93. Pin 1, clock A. So there's clock A and clock B. This part's a little weird-ish. Where's the good? There's a good, better picture. So here's the 93. The first stage, clock A on pin 14, just goes to A out. The second clock on B feeds a daisy chain set of outputs. So depending on how you clock A and B to the outputs over here, you can get different patterns of counting. So our clock is coming in pin 1. And why is it a double set of pins? Give me 1 sec here. Pin 1, pin 1. Huh. For some reason they're showing pin 1 and pin 8 in parentheses, but I don't see any packages where that's hooked to pin 8. So that must have been maybe an older package or different. Don't know. So I'm going to go with the first set of numbers because those make the most sense. So pin 1 is my input clock, and it ripples through 9, 8, and 11. Well, pin 1 and pin 14, pin 1, 2, and 3, we need to know the states of them. Those are the control lines. So, pin 1's the input, we found that. 2 and 3 are hooked to each other, which are hooked to ground. So 2 and 3 are hooked to each other and to ground. Where's their truth table? Which make it count, because if they're both high, it'd stop counting. And now pin 14, which is the other input, I don't see a connection on the top, and I don't see a connection on the bottom. So I think he may just not be used. Now, bad to leave it floating. Yep, he's tied to ground, so he's not used. So that first flip-flop's just a whole big don't care. Now, what else do we got hooked up on here? Outputs 1, 2, 3, 4 over. 1, 2, 3, 4 over, which is the output to the other divider, and 1, 2, 3, 5 over is ground or power? Power comes in 5 over on pin 5. So pin 5, yep, power, pin 10's ground, and 4 over is QD. So